Well, welcome back for the fourth session. I think that I'll be able to get everything in on this one. I apologize in that last one. I want to go over some stuff at the first of this one. Seems like I had a little bit of a brain freeze, I guess you'd say. That seems to happen quite a bit. I don't know. Maybe everybody has that same problem. But when I go back and we had our probability, our P of X, let me explain this a little bit more. That's n factorial over n minus x factorial, x factorial. And we gave an example of how we calculated this. P to the x, q to the n minus x. So n is equal to the number of trials. So in the situation that we gave at the last of the session last time, there were 10 flips. X is equal to the number of successes, which was the number of heads that we got, which was 5. And then P was equal to the probability of the success. Q was equal to the probability of the failure. Okay, which was, remember that Q is equal to 1 minus P. So, and then the combination is going to be nx, p to the x, q to the n minus x. Okay, so let's do this one just to go back and make sure that we've got this taken care of. Let's go back and do this one again for the probability. We're going to flip the coin 10 times and we're going to get one head. See what that probability is. So P of 1 success, 1 heads, is going to be equal to a C of 10, taken one at a time, P to the 1, Q to the 9, okay? And so this is going to be 10 factorial over 9 factorial, 1 factorial, 0.5 to the 1, 0.5 to the 9. Again, we can add that together and we get 0.5 to the 10, and we'd already calculated that. So this is going to be 10 factorial, or 10, times 9 factorial over 9 factorial times 1 factorial, which is 1. That cancels. So this is just going to be 10 times that number that we calculated earlier, 0.00096765. Remember, that's 0.5 raised to the 10th power if my calculator was right. So that's going to give me a 0.009765, which is going to be, if you round this off, this is going to be close to, get that up where you can see it, sorry about that. That's going to be close to 0.01, which means that about 1/100th of a time you would expect to flip a coin 10 times. If you did it 100 times, flipped a coin 10 times, and 1 out of 100 of those trials, you would expect to get only 1 head out of that. The other thing that I want to make mention of at this point is something that we mentioned in the last one, at the bell-shaped curve. And a lot of times what we're going to do is we're going to say that anything that's out here in the tails, about 2.5% of the time over here and 2.5% of the time out here, add those together, and that's going to be 5% of the time, that if it occurs in the tails, then it's going to be considered to be a rare event. Now, it turns out that when we talk a little bit more about this, these points are going to be about 2 standard deviations away from the mean, in the negative direction and the positive direction. And so we'll hammer that home time after time after time, and so you'll get a chance to be familiar with that. Okay, so now I want to go back and talk about the mean and the standard deviation for the binomial. Okay, the mean is equal to NP. So the mean number of times that we'd expect to get a heads out of 10 flips times 0.5, we would expect to get an average of 5 heads every time we did that. Okay, the standard deviation is going to be the square root of NPQ. That means that the variance is equal to NPQ. Remember that the standard deviation is the square root of the variance. And so NPQ, that's going to be 10 times 0.5 times 0.5. So that is going to be 2.5 is the variance. And the standard deviation is going to be the square root of 2.5, which is probably 1. I forget what it is, 1.8 or something like that, I'm not sure. Okay, and then the end of this chapter, we conclude with something that's called the Poisson distribution. And just want to mention that just a minute. It's commonly used, where it's commonly used, it is used a lot in rare events such as a number of telephone calls at a business in a given time interval, number of accidents, number of birds in a nesting area, radioactive decay. It's used in a lot of situations to model physical things. But again, the point that we need to make about that is that it's a discrete probability distribution. It uses a whole number. Each one of those things are, one person comes up to the counter. Those kind of things. The next chapter is going to be on continuous. This chapter was on the binomial and the Poisson. Again, I'm going to end at this point and